morning, myself Yash Mishra, and today I will be teaching you optics for JEE Mains and Advanced. So let's start the topic optics. So first thing in this we will be studying of refractive index of an optical medium. Refractive index of an optical medium. So mu is defined as speed of light in vacuum divided by speed of light in that medium. Okay. Value of mu is always greater than 1. Okay. So how we will calculate? So we will having a speed of light in vacuum which is 3 into 10 power 8, and in the medium it is given suppose 1.5 into 10 power 8. So value of mu is 2. So like this we will calculate the value of mu. Okay. So what is optical medium? Optical medium. So optical medium is defined as a medium through which light rays can pass. So suppose that there is some medium and some light rays are incident with the speed v1. So through this optical medium they are passing like this. So suppose that in this speed is v2 and after come here the speed is v3. If these mediums are equal, so speed may be equal. Okay. So how we will define in this mu? Mu will be defined like C by v2, C by v1, C by v3 or v1. So like this we will define the mu, refractive index, in different mediums. So if any questions will come like this, so we can easily find the value of refractive index in the optical mediums. Okay. So this like this, if there are different optical mediums, suppose that here it has a here the refractive index is mu2, here refractive index is mu3, here refractive index is mu4. So what will be the value of v? So value of v2 will be equal to c by mu2. Here the velocity will be v3 is equal to c by mu3, and here velocity v4 is equal to c by mu4. So like this, if different optical mediums are given and we have to find the velocity, like this we can find the velocity in different optical mediums. Our topic is what happens when light ray is incident on an optical medium. So we will see. So suppose this is a optical medium. Suppose it has a refractive index mu and a light ray is incident on it. So when the light ray is incident, then some part of will be reflected and some part of it will be transmitted and maybe some part may be absorbed by the medium. So in this 100% reflection is possible. 100% reflection is possible, but 100% transmission is not possible. 100% transmission is never possible. Okay, so we can understand. Suppose a light ray is coming like this, then how it will be transmitted like this, and how it will be reflected like this. So there will be a phase change after reflection. Here there will be no phase change. Okay. So and so there here suppose that the wavelength is lambda 1, here it is lambda 2, and suppose that the source has frequency f. So the frequency will never change. Frequency of all the three waves will be same. Frequency of all the three waves will be same. Okay, so frequency depends only on the source, not on the medium. So this we can remember if it is asked. So we can tell frequency depends only on the source and not on the medium. Okay, so coming to the Snell's law. So according to the Snell's law, we can find the relation between the incident ray and the transmitted ray to the second which is transmitted to the second medium. So suppose that there is a which has a velocity v1, and suppose that in this it has a velocity v2, and this is a medium bound ray. So by the Snell's law, suppose that it is making angle theta 1 and it is making angle theta 2. Okay, so mu1 sine theta 1 is equals to mu2 sine theta 2 by the Snell's law. So how it came, we will prove. So mu1 is the refractive index of the first medium, mu2 is the refractive index of the second medium, theta 1 is the angle which is made by the ray which is incident by the perpendicular plane of the medium boundary of the two mediums is theta 1, and made by the second ray is theta 2. Okay, so by the Snell's law we can find this relation, and all these lines, this normal line and this incident and which is transmitted, the ray which is in second medium, all these three rays lie in a same plane, So what it means, suppose that a ray is going in xy plane, suppose that it is a xy plane. So suppose that it is going like this. So when it will be going in the second medium, it will not come out of the plane, or not it will go inside the plane. If it is striking on the medium boundary, it will not come out or go in, it will be just in the same plane. Only the angle of that ray will be changed, and not the plane will be changed. It will be a rotation within the 360 180 degrees of in that same plane only, no, and it will not come outside, or nor it will be going inside the plate after striking in at the medium boundary between the two surfaces. So this is a very important law. Just we have to remember this relation for solving the questions in the exam. Only this relation, if we will be remembering, then we will easily solve. We can easily solve the questions which are there. mu1 sin theta 1 is equals to mu2 sin theta 2, and we can also remember that all the three rays are in the same plane. Okay, so how it came, we will be proving this. So proof. So according to the Fermat's law, when a light ray is moving from one place to the second place, suppose that this is the point A and this is point B. Suppose that it is moving from here to here. So it will always be moving on a path which is taking minimum time. So suppose that it is moving from A to B, so it will always take a path that is taking the minimum time. So how it will improve? So suppose that it has a distance L1 and it has this distance is L2, and suppose that this whole distance is L. So suppose that this is X and this is L minus X. Okay, so we will be writing the time taken by the wave, time. So distance upon, this is a distance X and this is a L. So what is this distance? X square plus L1 square. So what is this distance? And L2 square plus L minus X ka whole square. So what is the time? So suppose that it has a speed v1 and here it has a speed v2. So distance under root x square plus L1 square upon v1 plus under root L2 square plus L minus x ka whole square upon v2. Okay, so this is the time and we have to minimize this. Okay, so this is the relation. So dt by dx we will be putting equal to 0. So differentiating v1 is common, so 1 by v1 1 upon 2 root x square plus L1 square into 2x plus 1 by v2 1 by 2 root L2 square plus L minus x ka whole square into 2 into L minus x and 1 minus sign. So here it will be minus equal to 0. So this 2 and this 2 cancel, and this 2 cancel. So 1 by v1 xy under root x square plus l1 square is equals to l minus xy v2 into root of l2 square plus l minus x का whole square. Okay, so if we will see in this theta 1 and this is theta 2. So what is sine theta? Sine theta 1 is L1 upon under root L square plus x square perpendicular upon hypotenuse, and sine theta 2 is L2 upon under root L2 square plus L minus x का whole square. Okay, so if we like this we are getting the relation, and if we will try to solve, we have to include the angles in this, like sin theta, cos theta, then also it will be simplified, else it will not be simplified. So we can see in this, if we will be like multiplying in this further, it will not be simplified. So we have to include the angles in this. So what we are including, sin theta angles in this. Sin theta 1 upon v1 equals to sin theta 2 upon v2. So by the help of the Fermat's law, we have found this relation of the Snell's law. So what was a fundamental thing, that the light will travel always on the path which is taking the minimum time between the 2 points. So this is on this. So we will be differentiating the time with respect to the distance x, and we will be putting 0, and then we are getting this relation from that. Sin theta 1 by v1 is equal to sin theta 2 by v2. How? By introducing the angles in that relation. So now we will see the application of Snell's law. So in the application of Snell's law, so what will be seeing? The first application is, for example, the observer is here, and suppose a coin is in a water. Water. This is air, and this is observer. So always the light ray will be coming from the observer and going to the coin. But what will happen? Because the water is more dense than the air, there will be a shift in the distance which the observer will see, and that distance is h1. So suppose that this original distance was x of that coin in the water. Original depth was x, but what it will see just h. And suppose that air has a refractive index mu1, water is at refractive index mu2, then this distance which the observer sees, which is h, is equal to mu2 by mu1 into x. So the observer will see this distance, which is the apparent distance, not the actual distance of the coin. The observer will see the coin at a upper position than the coin, real coin position at which the coin is present. Okay, so like this, the apparent and real positions will differ when the refractive index of the medium will change. So this is a application of the Snell's law, which we can see. If that mu1 and mu2 are same, then this x and h will be same. If mu1 and mu2 are same, then this h and x will be same, because mu1 and mu2 will be cancelled. And we can see that if it is a air and air, if it, and somehow we maintain the refractive index of this water as mu2, which is same as that of the upper medium, air or some other medium, so we will be seeing at the same distance. But if it is a different, then we will see at other distance. If mu1, if this mu1 will be larger than this mu2, then we will be seeing the coin at a much lower depth than the actual depth at which the coin is present. So this can also happen, that coin will be seen at the upper distance, or it can also be seen at the lower distance at which the coin is present. So both things can happen in this, and coin can also be at the upper distance and it also can be at the lower distance. Okay. The generalizing the results when the observer is directly above the object. Generalizing the results when the observer is directly above the object. So suppose that this is a observer and this is object, and this is a refractive index mu1, this is refractive index mu2, this is refractive index mu3, and this is refractive index mu4. So at what distance this observer will see that object? So what will be the H apparent? So we'll be dividing this problem in parts. So firstly we will see, if observer is here, what will we see? What is the distance it will see that object from here, and then what will be the x apparent from here, then what will be the x apparent from here, and what will be the x apparent from here will be same as the x apparent from here, because the mediums are same. So first, second, third, 3 times will be applying. So in this, what will be, so suppose that this is a distance h1, this is distance h2, and this is distance h3. So what will be the x1 apparent? It will be mu3 by mu4 into h1. Okay. So what will be x2? It will be mu2 by mu3 into h2 plus x1. Okay, h2 plus x1. And what will be this x3, which is h apparent, will be mu1 by mu2 into h3 plus x2. So this is the H apparent which is seen by the observer from here. So in this we will be, so if we will be getting the final result, so we will be putting this x2 and in this x1. So how we will get, we will be seeing. So what is this H apparent? Is mu1 by mu2 into h3 plus x2 equal to mu1 by mu2 into h3 plus mu2 by mu3 into h2 plus x1 equal to mu1 by mu2 into h3 plus mu2 by mu3 into h2 plus mu3 by mu4 into h1. So this is the final result. So this is the final result. If there are so many medium boundaries and they are separated by different refractive index mediums, then this is the approach we will be following for this type of question. This is a application of the Snell's law only. So now I think the Snell's law thing is very clear to you all. Is one object A and there is one plane mirror. Okay, so there is one object and there is one plane mirror, and this is that image of this object. So and this observer is, for example, in a aeroplane observer. So it is moving like this. So till where it will be getting its image. So its image is this. So till where it will be seeing this image of object A. So this is image. So till where? So first, for example, this is the first ray. So till the time where it will be getting the images of this object A, so till the time it is getting these images of this object A, these reflected rays. So till the time it is getting reflected rays, it will see object A. So till the time it is getting reflected ray, so till which time this will be the last ray at this end point of this mirror. This is end point of mirror. So when the last ray will be there, this is the last ray. So from the last ray is the ray which is at the end point of the mirror, and then when that reflected ray of that ray will be approaching the aeroplane, the observer sitting in the aeroplane will be able to see that image. That will be the last image of the object A which he will see in the mirror. After that point, when it will be getting this last ray, after that point it will not be able to see the image of that object A, because all the rays will be incident like this and they are not incident on mirror, their incidence will be not on the mirror but on the water. So it will be not getting this image B. Okay, so this was the problem which we solved. So now we will be studying the concept of apparent relative velocity. That to A will be mu1. Mu1 is the refractive index in which observer A is present. So mu1, and this is x1, this is x2. So x1 by mu1 plus x2 by mu2. Okay, so this is the apparent distance of B with respect to A from the medium first in which A is present. Okay. Okay, so now we will be differentiating this d of x with respect to VA with dt with respect to t is mu1 dx1 by dt upon mu1 plus dx2 by dt by mu2. Okay, so which is mu1 v1 by v1 dx1 by dt is v1 velocity of first object, and dx2 by dt is v2 by mu2. So v of velocity of B with respect to A will be mu1 v1 by mu1 plus v2 by mu2. This is the apparent distance of B with respect to A. This is the apparent velocity of B with respect to A. So if we will differentiate, or if we want to calculate the acceleration of B with respect to A, acceleration of B with respect to A will be mu1 dv1 by dt by mu1 plus dv2 by dt by mu2. So which will be mu1 a1 by mu1 plus a2 by mu2. So if we want to calculate relative distance, we saw how to calculate. If we want to calculate relative velocity, this is the formula v1 by mu1 plus v2 by mu2 into in which the observer is present. So acceleration of B with respect to A will be mu1 a1 by mu1 plus a2 by mu2. So for example, the observer is present in some medium which has a refractive index mu3. So here we will be writing this mu3. Like this we will change, and we want to calculate the apparent distance of the object like C, and object A is present in mu3, so we will do like this. Okay, so this is the concept, and same by differentiating apparent distance we will get apparent velocity, and by differentiating apparent velocity we will get apparent acceleration of B with respect to A.